Hi, pre-calculus students. Welcome to section 6.3a on vectors in a plane. You have fill-in notes that I gave you in class, or you can see on Schoology. So we're going to go ahead and fill these notes in together. So I'll go ahead and share my screen. Here we go. I think you'll find that vectors are really pretty easy to use, again, just because it's our first time learning it, that the math and the concepts are pretty easy. There's just a lot of different concepts. So, but I think you'll find it is a lot simpler than some other things we've done. So what is the definition of a vector? It is you may have studied vectors in physics. In fact, you probably did. It is a directed line segment that has a magnitude that's represented by its length, and it has a direction. Which will be indicated later by theta. We also use an arrow on the directed line segment, but later on we will be using theta, which means that we will be using trig. Trig is just everywhere, isn't it? And it's used to show the direction of a force generally. Used to show the direction and magnitude of a force, such as velocity. And so here is a picture of what could be a vector. My first point I drew here could be an initial point, and we will call that point P, and we will put initial point. And the tail, which is the terminal point, we will call Q. Tail is the tail is the terminal point. And the order of those points does matter because it changes the direction. And we can label this vector either the vector PQ, again, where you write the initial point first and the terminal point second, with a arrow with a line segment with a half arrow above it, or we use a bold letter such as U, V, and W usually. So this vector could be named vector PQ or bold lowercase vector u. So what are some types of vectors? There is a zero vector. A zero vector has no magnitude. Now you may be like, okay, well, if there's no magnitude, then there's no force. So why would we need a zero vector? Because often we're looking to put vectors in equilibrium to create a zero vector, and that would create a vector with no magnitude. So we'll take a vector and add to it its equilibrium vector to get a zero vector. Now, opposite vectors have the same magnitude, they are parallel when drawn, but opposite directions by 180 degrees. So they are not equivalent. So we'll put not equal vectors. So let's get to what equivalent vectors are. They have the same magnitude and direction. There we go. And a unit vector has a magnitude, is any vector that has a magnitude of 1. We will be writing unit vectors. All right, so number 3, how do you write a vector in standard position? That is called component form. Okay, so the idea behind that is there are an infinite number of vectors in the universe that you could put on a plane that have an initial point and a terminal point. And when you draw them, they have the same direction and the same magnitude, right? But different starting and stopping points. So we should be able to represent that infinite number of vectors with a standard, a vector in standard position or in component form. And what we're going to do then is we are going to represent all those vectors that have the same magnitude and direction as a vector in component form. Its initial point will start at 0, 0 instead, and its terminal point will decide the magnitude and direction. So how do we do that? Write the vector with initial point 1, -2, and a terminal point 3, 4 in component form. So here's what we're going to do. So our vector, our initial point 1, -2, we're going to call P1 and P2 because it is that initial point that we made back in our drawing. And then the point 3, 4, we're going to call Q1 and Q2 because that's how we labeled the terminal point in our last drawing. So to make a vector in standard position, let's call it lowercase bold v, is equal to. In component form, we are going to do a side caret, which is on your computer. So V1 will be our horizontal value, our X value if we are on a plane, and comma, our V2 will be our vertical component, which with a side caret on a plane. Okay, so it's really an XY point if you put it on an XY plane, but it's a horizontal and vertical component that we call V1 and V2 because it is related to a vector. And where that comes from is we will do terminal minus initial, Q1 minus P1. So notice we took the two horizontal components of the terminal point and the initial point and we subtracted them. Then for V2, which is the vertical component, we will subtract the vertical components of the terminal point and the initial point. And again, where the order does matter. So really nice, simple math. So here we go. Q1 is 3 minus P1 is 1, comma, Q2 is 4 minus P2 is a -2. And our final vector in component form is 2, 6. So notice a vector in component form only has one point listed, its terminal point, because in standard position, or component form, its initial point is 0, 0. So let's draw that. So below, draw the vector with the initial point 1, -2 and terminal point 3, 4. And then let's draw it in standard position, which is right here, the vector 2, 6. Okay, so the vector 1, -2 has a starting point right there. There we go. And a terminal point of 3, 4. 3 and 4. Here we go. Let's connect those. That's supposed to be straight. There we go. So there's our vector with an initial point of 1, -2 and a terminal point of 3, 4. Now let's draw it in standard position. It has an initial point of 0, 0 and a terminal point of 2, 6. So if you notice, these vectors are the same length, right? And have the same direction, but one is in standard position. Okay, let's go a little further. How do you find the magnitude of a vector then? Right, since we've been talking about it so much and it's an important part of its description. So find the magnitude of the component form of the vector from number 3. So the magnitude of a vector v. So here's our vector v, and ours was v1, right? v1, v2, and our vector was 2, 6. So if you notice from the drawing above, our vector 2, 6, definitely you could make it the hypotenuse of a right triangle. And to find its length, you could use the Pythagorean theorem or the distance formula, where the one point is 2, 6 and one point is 0, 0. So in other words, to find the magnitude of vector v. So the way we show that is with double lines around the v. That means you're being asked to, or we are providing the magnitude, is the square root of the horizontal component squared plus the vertical component squared. It's really that easy. So our vector is the square root of 2 squared plus 6 squared, which is the square root of 40, which is 2 square roots of 10. Nice and easy. Now, how do you write a unit vector? Here's number 6. How do you write a unit vector that has a magnitude of 1 in the same direction as a given vector? Use the component form of the vector from number 3 to write its unit vector. So, given a vector v, v1, comma v2, the way you make it a unit of 1 is to find the magnitude and divide the v1 and the v2 by the magnitude of v. If you do this, you will have a vector in the same direction, but its magnitude will be a unit of 1. So let's do that with our vector v, which was 2, 6. Here we go. So that would be 2 divided by 2 square roots of 10, 6 divided by 2 square roots of 10. Here we go. We can reduce that a little bit to 2 over, whoops, that would cancel out. Let's see if I can erase a little bit. There we go. That would be 1 over the square root of 10. And 3 over the square root of 10. And if you rationalized by multiplying the numerator and the denominator by the square root of 10, we would have the square root of 10 over 10 and 3 square roots of 10 over 10. If you took the time to find the magnitude of this vector, the square root of 10 over 10 comma 3 square roots of 10 over 10, you would find that you have a vector with a magnitude of 1. Let's go to number 7. Geometrically, how do you add two vectors? How do you subtract them? And how do you double a first vector and add 1/2 of another vector? So we're going to call adding the two vectors A, subtracting them will be B, and we're going to double the first and add 1/2 of the second is C. So let's take a look. Let's make two very different vectors. Here's my vector U, and I will make my vector V go kind of in the opposite direction and a little longer. That's supposed to be straight. There we go. Here's vector V. There we go. So how do we add the two vectors? Let's come on down here. Simply, and when I draw vector U and V, they are supposed to be equivalent to the vectors I drew above, but you know they may not be perfect. Okay, so let's take our vector U, and the way you add V to it is you move it, you keep its direction the same, and simply move it down so that it is on the tail of U. So here is, I'm adding vector V, right? I literally added V onto the end of U, right? And my resultant vector starts at the initial point of U, my very starting point, and goes to the very end point. And I will draw a dashed vector to show that. This is called my resultant vector. So this shows just like if you walked in the direction with this velocity of U, and then you switch direction, right, and walked with a higher velocity V, the resultant vector shows where you would begin and where you would end. Okay, now how do we subtract the vectors? Let's take vector U again. Vector U. Now, if I were to add on vector V, I would come down to the right. But the opposite would be, so U minus V is really U plus a negative V. And the negative indicates that I'm going to draw V just as long, but in the opposite direction. So there's U minus V. My resultant vector starts at the initial point of U and ends at the tail of V. Okay, how do we double a first vector and add 1/2 of another vector? Okay, so when we're doubling U, that means we keep U in the same direction, but we make it twice as long. So here is 1U, 2U's. So here is 2U. When I take 1/2 of V, I'm going to add it. So I'm going to put it onto the tail of 2U. V, I will keep in the same direction, but make it 1/2 as long. Here's 1/2 of V. And my resultant goes from the initial point of 2U to the tail of a 1/2 V. Here we go. So algebraically, how do we add vectors? How do we subtract them? how do we double and triple a vector and subtract them? And so it's much easier than drawing them and much more accurate. So let's go ahead and do that. So we are going to use vector u as 1, 4, and vector v is -2, -3 for these operations. So let's add those vectors. And the way you would do that is simply write vector u plus vector v There we go. And the way we add them is simply add the horizontal components, comma, and add the vertical components. Here we go. So our resultant vector is -1, 1. How do we subtract? Here is our vector 1, 4 minus -2, -3. And we will subtract the horizontal components, and we will subtract the vertical components. Two negatives make a positive, and we get 3, 7. How do we double a vector and triple a vector and subtract them? So let's do 2 times 1, 4 minus 3 times vector -2, -3. Okay, we are simply going to do 2 times 1 minus 3 times a -2. So we are simply multiplying the horizontal components by their scalars 2 and 3 and subtracting them. For the vertical, 2 times 4 is 8 minus 3 times a -3 is -9. Right? And our resultant vector is 8, 17. Here we go. All right, number 9. How do you write a vector in component form as the sum of unit vectors? What is the vector I and what is the vector j? And use the vector in number 3 to write the form of the sum of the unit vectors. So the first thing, that vector, if you remember, was 2, 6. Here's what I would want you to know. This is component form, right? V1, V2. The sum of unit vectors is simply these horizontal and vertical components times I and j. So the sum of unit vectors instead of component form is as easy as 2I would be the horizontal component plus, notice it said sum of unit vectors, 6j. It really is that easy. Now, vector I is known as the vector 1, 0, and vector j is known as the vector 0, 1 in standard position. So here is a picture of vector I here, and vector j is here. right? So the reason why this is vector 2, 6 in component form and the same vector in unit, sum of unit vector form is if I took 2 and multiplied it by vector I, which is 1, 0, and added it to 6 times vector j, right? Notice I get the vectors 2, 0 plus the vectors 0, 6. And when you add them up, you get the vector 2, 6. So the way you write a vector in component form into the sum of unit vectors is just to take the horizontal value and the vertical value, multiply it by I and j and add them up. It really is as easy as you would think. Okay, let's do some examples. Number 12 from the book. Show that U and V are equivalent, where U has the initial point 0.04 and terminal point -3.4, and V has the initial point 0.33 and terminal point 0, -5. And there is a picture provided in the textbook. So I'll go ahead and draw that. You know it won't be the best thing you've ever seen, but let's do it. 1, 2, 3, 4, 5, 6. Okay, so the first vector has an initial point of 0, 4. There we go. And a terminal point of -3, -4. Let's see if I can do a little erasing there. -3, -4. Right. And I'll try to connect them well. Here we go. And the other vector has the initial point 3, 3. So right here. And a terminal point of 0, -5. Okay, so when you see these vectors in the book, well, I didn't do that bad. They appear to have the same magnitude and direction, okay? So how do we prove that? Well, let's first find the magnitude of the direction of each vector and then compare them. Notice that, let's write each vector in component form. So the vector on the left in component form would be -3 minus 0 and -4 minus 4 is -8. The vector on the right in component form would be 0 minus 3, comma, -5 minus 3, -8. Notice, obviously, if I find the magnitude, right, of both of these vectors, now you can see they are the same vector in component form. So they must be equivalent vectors. Because they are the same vector in component form, right? Notice that, of course, they would have the same magnitude because I would apply the same formula. And they obviously have the same slope, right? If you do the slope formula on each, they have the same slope. That doesn't make their directions equivalent, but the fact that the arrows are pointing in the same direction does. So they are parallel, same slope, same direction arrows. Right, and obviously the same magnitude. So they are equivalent. Last problem, find vector v. This is number 50 in your book. Find a vector v with a magnitude of 3 with the same direction as vector u, which is -12 and -5. Well, let's take a look. What if vector u really does have a magnitude of 3? Then, right, vector v would be the same as vector u. So let's get the magnitude of u, which is -12 squared plus -5 squared. I'm going to add them up and take the square root, which is 13. Okay, so no, vector u has a magnitude of 13. So what am I going to do? Well, I want to keep the direction of magnitude u. So I am first going to keep magnitude u. And I know how to make it 1 unit long by dividing it by its magnitude. So now this is vector u with its own particular direction, 1 unit long. So if I just multiply it by 3, I've now forced it to be 3 units long. So this vector then would be a -36/13, comma, -15/13. This is the vector with the same direction as u, but has a magnitude of 3. So as you can see, there's tons going on in section 6.3, but really kind of easy, really. You know, subtraction, little multiplication. So give the assignment a try, and I hope it goes well for you, and then I'll help you also.